In this video today, I will discuss paper 2 AS level structured questions from March 17, question paper 2. Number 1, complete figure 1.1 by putting a tick in the appropriate column to indicate whether the listed quantities are scalars or vectors. Remember that scalars are quantities that have no direction. Vectors are quantities which have direction and also a magnitude. Yeah, so acceleration, this is vector. Force is a vector. Kinetic energy, it is a scalar. It does not have any direction. Momentum is vector. Power and work are scalars. B, a floating sphere is attached by a cable to the bottom of a river as shown in figure 1.2. It is forming an angle of 75 degrees to the horizontal riverbed. Assume that the force on the sphere due to the water flow is in the horizontal direction. So the direction of the flow of water is horizontal. The radius of the sphere is 23 centimeters and it is made from a material of density 82 kilogram per meter cube. Show that the weight of the sphere is 41 newtons. Weight is mass times g, so we have to find the mass first because it is not given. And we know that rho equals m over v, so mass is volume multiplied by density, rho. So mass is equal to 4 over 3 pi r cubed. This is the volume of the sphere multiplied by the density. R is given 23 centimeters, 0.23. And the density is 82 in SI unit. So we can calculate that the mass is 4.179 kilograms and weight itself is mass times g. So we multiply by 9.81, we got 41 newtons in two significant figures. Now the tension in the cable is 290 newtons. We want to determine the upthrust acting on the sphere. I want to draw all the forces that act on the solid sphere here. I have this tension of the cable, and I can resolve this, I have the weight, and now I want to resolve this tension into T times the sine of 75 degrees, and this is T times the cosine of 75 degrees. So here I have one more force, which is the upthrust. This is the upthrust, the direction is upwards. When we want to find the upthrust, we know that this system, the solid sphere, is in equilibrium. So we can see that the resultant of forces on y-axis is equal to 0. So I have here upthrust and T times the sine of 75 degrees and weight. Yeah, so upthrust is equal to the weight plus T times the sine of 75 degrees. The weight has been calculated, tension is given, 290, and theta is 75 degrees. So I can find the upthrust to be 321 newtons. Explain the origin of the upthrust acting on the sphere. Upthrust will occur because the pressure on the lower surface of the sphere is greater than the pressure on the upper surface of the sphere. So there is something like lifting force, yeah, we call that upthrust. Number 2, state the principle of conservation of momentum. The principle of conservation of momentum is the total momentum of objects before the collision is the same as the total momentum of objects after collision. You have to state this provided no external forces, or you can say in a closed system, or you can say in an isolated system. 2b, two blocks A and B are on a horizontal frictionless surface. The blocks are joined together by a spring. Yeah, as shown in the figure, you are given the masses of the blocks, 4 kilograms and 6 kilograms, and the variation of F with the extension X of the spring is shown in this figure. The first question is about the elastic potential energy of the spring at an extension of 8 centimeters, you have to show that the value is 0.48 joules. So we have to see it from the graph, because we know that potential energy is equal to the area under the graph. So when the extension is 8 centimeters, we have to find the area of this triangle. Yeah, elastic potential energy is equal to the area under the graph. It is equal to a half times 8 centimeters, 0.08 meters, multiplied by this is 12 newtons. So it is 0.48 joules. The blocks are released from rest at the same instant. When the extension of the spring becomes 0, block A has speed VA, block B has speed VB. For the instant when the extension of the spring becomes 0, use conservation of momentum to show that the ratio of the kinetic energy of A and B is 1.5. The conservation of momentum is MAVA plus MBVB equals MAVA prime plus MBVB prime. If we see this diagram, MA is 4, but VA is 0 because the blocks are released from rest. MB is 6 kilograms, but VB is also 0. So I have 0 plus 0 equals MA 4 multiplied by this VA plus 6 multiplied by VB. Yeah, so now we have the ratio of VA and VB. Yeah, actually one of them is negative, but that's only because of the direction. We know that block B will move to the left while block A will move to the right. They move in opposite direction. So VA over VB is 6 over 4, and kinetic energy is a half mv squared. So a half MAVA squared over a half MBVB squared. We can cross this a half, and then MA is 4, MB is 6. VA over VB is 6 over 4, this one. Yeah, so now we have 2 over 3 multiplied by 3 over 2 squared, and we'll get 1.5. The next question, use the information in BI and BII to determine the kinetic energy of block A. It may be assumed that the spring has negligible kinetic energy and that air resistance is negligible. Yeah, we know that the elastic potential energy of the spring, it is from the kinetic energy of A and the kinetic energy of B when they are released. And from BI, we can see that the elastic potential energy is 0.48 joules. From BII1, we have calculated that kinetic energy of A divided by kinetic energy of B is 1.5. So kinetic energy of B is 2/3 kinetic energy of A. So when I have this equation, the conservation of energy, or the elastic potential energy is gained from the kinetic energy of both objects, then I can substitute this using this number 0.48. Kinetic energy A plus kinetic energy B can be substituted using this 2/3 kinetic energy of A. So I have now 0.48 equals 5 over 3 kinetic energy of A, and I can calculate that kinetic energy of A here. Oh, sorry, this should be kinetic energy of A. It is 0.288 or 0.29 joules. The next question, the blocks are released at time t equals 0. On figure 2.3, sketch a graph to show how the momentum of block A varies with time until the extension of the spring becomes 0. Numerical values of momentum and time are not required, so we can see here that initially they are at rest. So we will start the graph later from 0. Yeah, and then because the initial momentum is 0. And then the velocity decreases as time increases. And delta v over delta t decreases because velocity decreases as time increases. So this is acceleration. Acceleration will decrease, and acceleration is proportional to f, while f itself is delta p over delta t, which in this graph will be the gradient of the graph. So we will draw a curve from the origin with decreasing gradient until when the extension of the spring becomes 0, then there will be no force anymore, there will be no acceleration, so we have this curve until it is flat like that. Yeah, until the gradient is 0. Number 3a, divine velocity. Velocity is the rate of change of displacement. B, a car travels in a straight line up a slope as shown in figure 3.1 here. The car has mass 850 kilograms, travels with a constant speed of 9 meters per second. The car's engine exerts a force on the car of 2000 newtons up the slope. Yeah, the F is 2 kilonewtons or 2000 newtons, the F of the engine. A resistive force Fd due to the friction and resistance opposes the motion of the car, and the variation is given here in the figure 3.2. Now, state and explain whether the car is in equilibrium as it moves up the slope. I think we have to see this, that the velocity here is constant speed of 9 meters per second. So I can say that because it is moving at constant speed, then the car is in equilibrium because the resultant force is 0. Consider the forces that act along the slope. Use data from figure 3.2 to determine the component of the weight of the car that acts down the slope. Here, I would like you to see when the velocity is 9 meters per second, what is the drag force that is acting? It will be 0.4 in the unit of kilonewtons. Yeah, so I want to write this down, that Fd is 0.4 kilonewtons when the speed is 9 meters per second. And I want to draw the forces that act on the car. We have the weight, and this is the x component of weight, and this is the y component of weight. We want to determine this Wx. Yeah, and we have this drag force, which direction is opposing the direction of motion. This is the drag force. So I can now I can make an equation. The resultant of force is 0. So this F of the engine that is bringing the car upwards there, up the slope, will be equal to this horizontal component of weight plus this drag force. Yeah, because the resultant force is 0, then the forces that moves in x direction, the resultant will be 0. So this F is given 2 kilonewtons, 2000 newtons. We want to find Wx, and that drag force at that time is 0.4 kilonewtons. So I can calculate Wx, or the component of weight of the car that acts down the slope, is 1600 newtons, or 1.6 times 10 to the 3 newtons, or 1.6 kilonewtons. Yeah. Show that the power output of the car is 1.8 times 10 to the 4 watts. We have this equation, P equals F times V, and the F of the car is 2000 newtons multiplied by 9. It is equal to 18,000 watts, or 1.8 times 10 to the 4 watts. The car now travels along horizontal ground. The output power is maintained at the same power. The variation of the resistive force acting on the car is given in figure 3.2. And we want to calculate the acceleration of the car when its speed is 15 meters per second. So now we have to see this graph one more time. When v is 15 meters per second, then we can read that the Fd, the drag force, is at this point, and this will be 0.66 kilonewtons. Yeah, that's the data that we need from the figure 3.2. So Fd is equal to 0.66 kilonewton, and P equals F times V. The driving force itself is this P, power 18,000, divided by 15. Now the driving force is 1,200 newtons only. Before it was 2,000 newton. Yeah, so because we have F equals mass times acceleration, this F will be the driving force subtracted by the drag force. The drag force is 660 newtons, 0.66 kilonewtons. The mass is 850. We can find the acceleration to be 0.64 meter per second squared. Number 4, state what is meant by the Doppler effect. The Doppler effect is the change in observed frequency when a source of wave moves relatively to the observer. Yeah. B, a child sits on a rotating horizontal platform in a playground. The child moves with a constant speed along a circular path as illustrated in this figure. An observer is standing a long distance away from the child. During one particular revolution, the child, moving at speed of 7.5 meters per second, starts blowing a whistle at point P and stops blowing it at point Q on the circular path. And the frequency of the sound is 950 Hz. The speed of sound is given. Determine the maximum frequency of the sound heard by the distant observer. Maximum frequency of the sound will be given by this equation. F of the observer is equal to F of the source multiplied by V divided by V plus minus Vs. When we want to find maximum frequency, then this should be negative because the value of this should be the smallest. Yeah, so we have this 950 multiplied by this 330 divided by 330 minus this speed 7.5. And it will be equal to 972 Hz. If you want to write it down in two significant figures, it will be 970 Hz. Now, describe the variation in the frequency of the sound heard by the distant observer. Because it is moving like this in a circular path to a distant observer, so there is a change in frequency. The maximum frequency we have calculated. And now I want to find the minimum frequency. The minimum frequency, of course, Fs multiplied by V divided by V plus Vs here. So I got 929 Hz. So the distant observer here, he will hear that the frequency decreases from 972 Hz to 929 Hz. Number 5, an electron is traveling in a straight line through a vacuum with a constant speed of 1.5 times 10 to the 7 meter per second. The electron enters a uniform electric field at point A, as shown in figure 5.1. The electron continues to move in the same direction until it is brought to rest by the electric field at point B. Distance AB is 2 centimeters. State the direction of the electric field. We know that positive charges experience an electric force in the same direction as the electric field, and negative charges experience an electric force in the opposite direction as the electric field. We can say that the direction of an electrical field at a point is the same as the direction of the electrical force acting on a positive test charge at that point. So I can say that it is from the positive to the negative. So I will just assume that this part of the electric field is the negative, and this part is the positive. So the electric field will be directed from the positive to the negative here. This is the direction of the electric field lines. And then when there is an electron placed in that field, it will experience a force that is in opposite direction to the direction of the field, the electric field. So when this electron is placed inside, it will experience a force to that direction. So of course it will be accelerated, not stopped at B. So this is not the case. Yeah, the case is, I assume that this has positive charge and this has negative charge. So the electric field will be directed from the positive to the negative there. This is the direction of the electric field lines. And when we place electron inside, the electron will experience a force that is in opposite direction to the direction of the electric field. So it will experience a force to the left. That's why it will be stopped here at B, at point B. So I can say here that the direction of the electric field is from A to B, from the left to the right. Next, calculate the magnitude of the deceleration of the electron in the field. We know that it will experience a deceleration because the force is in opposite direction to the direction of the field. And we can use this equation, v squared equals u squared plus 2as. V is given 1.5 times 10 to the 7. U is 0 because it starts moving from rest. And the distance it traveled is 2 centimeters. Yeah, so we have here the acceleration to be 5.6 times 10 to the power of 15 meter per second squared. This is negative because this is the deceleration. Yes, so this should be negative. Calculate the electric field strength. The equation for electric field strength, or the definition, is force per unit charge. And the force itself is mass times acceleration or deceleration. So you can calculate E to be 3.2 times 10 to the 4 volt per meter. Because this is negative and the Q is also negative, then E will be positive here, yeah? And then the electron is at point A at time 0. On this figure, sketch the variation with time t of the velocity v of the electron until it reaches point B. Numerical values of v and t do not need to be shown. We know that it is moving from a certain initial velocity and it is moving at constant deceleration. Yeah. So this is the graph. Now, number 6. 3 resistors of resistances R1, R2, and R3 are connected as shown. They are connected in parallel. The total current in the combination of resistors is I, and the potential difference across the combination is V. So if it is connected, they are connected in parallel, then all get the same value of potential difference V. All have the same potential difference V. We want to show that the total resistance can be given by this equation. So we will start from this, yeah, connected in parallel. V is the same. So current is divided into 3. So total current will be I1 plus I2 plus I3. And I is V over R. V over R equals V over R1 plus V over R2 plus V over R3. They all have the same V, so we can divide this by V and we will get that equation. 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. B. A battery of EMF 6 volts and internal resistance R is connected to a resistor of resistance 12 ohms and a variable resistor X as shown in this figure. By considering energy, explain why the potential difference across the battery's terminal here is less than the EMF of the battery. Of course, because there is internal resistance there. Yeah, so the EMF will not be the same as the potential difference. So, and in the term of energy, EMF is the total energy available per unit charge, while there is energy dissipated in the internal resistance. So PD across the battery's terminal will not be the same. It will be less than the EMF. A charge of 2.5 kilocoulomb passes through the battery. Calculate the total energy transformed by the battery. from the definition before, EMF is the total energy per unit charge. So when we want to find the total energy, it will be equal to EMF multiplied by the charge. Yeah, the EMF is 6 volts and the charge is 2.5 kilocoulombs. So we will get 1.5 times 10 to the 4 joules. The number of electrons that pass through the battery, we can use this information. One electron is of charge 1.6 times 10 to the minus 19 coulomb. So when we want to find the number of electrons, it will be the total charge 2500 divided by the charge of one electron. It will be 1.56 times 10 to the 22 electrons, or if you want to write down in significant figure, it will be 1.6 times 10 to the 22 electrons. The combined resistance of the two resistors connected in parallel is 4.8 ohms. We want to calculate the resistance of X. Use the equation 1 over R equals 1 over R1 plus 1 over R2. Yeah, the total will be is 4.8. The other one is 12 ohms. So we want to find that Rx. You can calculate, then Rx will be 8 ohms. Use your answer in BIII to determine the ratio of the power dissipated in X and 12 ohms resistor. We use this equation P equals V squared over R. We have several equations for P. P equals V squared over R, P equals I squared R, and P is equal to VI. But in this case, I will use this. Why? Because we have a parallel connection. Yeah, we have a parallel connection. So here in parallel connection, V is the same. So when I use Px over P12 V squared over 8 divided by V squared over 12, I can just cross V squared out because they are the same. Yeah, so Px over P at 12 ohm is equal to 12 over 8. It will be equal to 1.5. The resistance of X is now decreased. Explain why the power produced by the battery is increased. Now, we will see that when X is decreased, then the total resistance will decrease. So the total current flowing later will increase because the total resistance decreases. And because the power of battery is V times I, and this I increases, so power will also increase. Okay, last number 7, a nucleus of bismuth 212 decays by the emission of an alpha particle and gamma radiation. State the number of protons and the number of neutrons in the nucleus. This 83 is the number of protons. So the number of protons is 83. Number of neutrons is this number of mass minus 83 minus the number of protons. So it will be 129. The gamma radiation emitted from the nucleus has a certain wavelength, 3.8 picometer. Calculate the frequency of this radiation. So the lambda is 3.8 times 10 to the minus 12 meter. Pico is a prefix. Yeah. So we have this equation F equals V over lambda. And this V is the speed of electromagnetic waves in vacuum. 3 times 10 to the 8 divided by the lambda. So you get the frequency. You can write it down into significant figures. Explain how a single beam of alpha particles and gamma radiation may be separated into a beam of alpha particles and a beam of gamma radiation. You have to know the characteristics of alpha particles and gamma radiation. It is alpha particles are positively charged, while gamma radiation is uncharged. Yeah, so I can use an electric field at a certain angle to the beam so that alpha particles will be deflected because they are positively charged, while gamma radiation will not be deflected because they are uncharged. The alpha particle emitted from the bismuth nucleus has an initial kinetic energy given. As the particle alpha moves, the alpha particles moves through the air, it causes the removal of electrons from atoms. and the alpha particle loses energy and stopped after removing 1.8 times 10 to the 5 electrons as it moved through the air. We want to find the energy in electron volt needed to remove one electron. First, we have to divide this energy by the number of electrons. That is the energy to remove one electron, but in joules. To convert joule to electron volt, we have to divide by 1.6 times 10 to the minus 19. Yeah, so we get 32.3 electron volts or 32 electron volts in two significant figures.